Welcome all. So, today we will be continuing our lecture on the analysis and design of structures subjected to blast and impact loading. Last time we saw the different capacity calculations. Okay. So, today we will continue with the design methods. Okay. So, moment curvature relationship of a beam. Moment curvature relationship simply determines the evolution of the stress distribution from elastic to fully plastic condition at the formation of hinge. Okay. Shape factor ratio. Okay. So, this is the ratio of the fully plastic moment to yield moment. Okay. And there is a bilinear moment curvature models that approximate the actual deformation response. Okay. So, we will try to look into what is moment curvature relationship. Okay. Let us say we have a cantilever beam. Okay. We have a cantilever beam and then we try to put a moment at the top, okay, an external moment at the top. Okay. So, then we will try to increase the value of this moment. Okay. And if we cut any section, okay, if we cut any section and look into the distribution of the stresses into this cross section, okay, with respect to the change in the curvature of the beam. Okay. So, this relationship between the moment and the curvature is called the moment curvature relationship. Okay. Basically, it determines the capacity of a section. Okay. So, it determines what is the moment carrying capacity of a particular section. Okay. So, let us say we have a beam. Okay. The beam is an I-shaped beam. Okay. So, when we start the loading in the beam, okay, let us say we are assuming that the loading is in the x axis, okay, along the stronger axis. Okay. So, the beam is serving a moment along the x axis. Okay. So, x axis becomes my neutral axis. Okay. The definition of the neutral axis goes like this: the axis in which the net strain is 0. Okay. So, at the starting what will happen is that at the two periphery, okay, if this is my cross section, this is my neutral axis. So, at the two peripheral zone, okay, strain will be developing. Okay. As we apply the moments, okay, as the moments are applied along the x axis, okay, and it is bending along the x axis, strain will be developed, okay, at the two ends. Okay. So, as we increase the applied moment, okay, this value of strain will keep on increasing. Okay. So, the value of the strain will keep on increasing. Okay. And we know that the stress is directly proportional to the strain, okay, till the section remains in the elastic region and it is following the Young's modulus. Okay. So, with this increasing stresses, okay, what we can do is that we can calculate the total area under the curve. Okay. So, this will denote us this is the strain profile. Let us say this was the strain profile. So, from the strain profile we can get the stress profile. Okay. From the stress profile, okay, if we integrate this distribution of the stress over the applied area, okay, if we integrate the stress over the applied area, okay, we will get the value of compressive and tension. Okay. So, this is C, this is T. Okay. And if we take the moment arm, okay, then we can calculate if we take this as the lever arm, okay, so we can calculate the moment that will be given by C times the lever arm. Okay. So, this way we can calculate the moment. Okay. So, the moment the increase in moment, okay, we can calculate with respect to the capacity of the section. Okay. So, similarly we can calculate the curvature of the section. Okay. So, firstly it will remain, if you look into the stress strain curve, okay, let us say this is for a steel type of material. Okay. The material used is steel. Okay. So, first of all, okay, the material will be remain in the elastic region. Okay. After the elastic region, okay, it will go into the plastic regime. Okay. So, we approximate this by an elastoplastic curve. Okay. So, once the elastic range is reached here, okay, then that outermost fiber has reached the maximum elastic strain. Okay. So, after that the elastic strain will try to propagate into the section. Okay. So, this propagation will be there. Okay. So, once this propagation is complete, okay, we say that the fully plastic region has been formed, okay, and we assume that a so called hinge formation occurs at this juncture, okay. So, this is the elastic region, okay. After that the elastic limit has been reached and this is being propagated into the other fibers, okay. So, here the outermost fiber, in the outermost fiber the elastic range has been reached, okay. Now, this thing is being reached in the inner fiber zone also, okay. So, once this things complete, okay, we say that the fully plastic region has formed and my system plastic hinge has been formed in my system, okay. So, this is how we differentiate between the elastic and the plastic region, okay, or formation of, this is how we also define the formation of plastic hinge, okay. Okay. So, here the stress distribution is evolving from elastic to fully plastic condition at hinge, okay. So, here it starts from the elastic region, okay. It is first of all it is less than the elastic region, then the elastic region is reached at the outermost fiber and after that it propagates into all the fibers, okay. So, from elastic region to a fully plastic condition is reached out here, okay. So, shape factor, okay. So, this is the ratio of the fully plastic moment to the yield moment, okay. So, this is the shape factor, okay. So, the ratio of the second moment of area in the plastic region to ratio of the second moment of area in the elastic region, okay. This is called the shape factor, okay. So, for I beams typically it is in the range of 1.15, okay. So, this bilinear moment curvature model, okay, approximate the actual deformation response, okay. This is how the deformation response is assumed, okay. For ductility ratio, okay, less than 3, okay, for ductility ratio less than 3, plastic moment is considered, okay, as occurring in between the fully elastic and the fully plastic region, okay. So, this is the intermediate region, okay. For ductility ratio greater than 3, we assume that the fully plastification has occurred, okay. So, this is the elastic region, okay, this is the fully elastic region, this is the fully plastic region. So, there is an intermediate region where the elastoplastic deformation is going on, okay. So, if the ductility ratio is less than 3, we assume that the system is in the elastoplastic region, okay. If the ductility ratio becomes more than 3, we assume that the fully plastification has formed, okay. And this is the shape of a typical moment curvature relationship, okay. So, y axis moment, x axis is the curvature, okay. So, this is the plot of the actual moment curvature relationship, okay. So, we use the bilinear design curves, okay, M1 and M2, okay. So, depending upon whether my section is lying in the fully plastic region, okay, M2 or elastoplastic region, okay, M1, okay, we draw two bounds for the region, okay, and each section will remain, okay, in between these two regions, okay, depending upon what is the ductility has been achieved in the region, okay, and this is the point denoting the elastic region, okay. So, from the elastic region it goes into the elastoplastic region and from the elastoplastic region it goes into the fully plastic region, okay. So, as the moment increases, okay, the system move from elastic to elastoplastic, this is the elastoplastic boundary, okay, it goes into the elastoplastic region and from there it reaches the plastic region, okay. So, depending upon the ductility, okay, the region can be determined, okay. So, this is an approximate way, okay, to get the estimate of the capacity of a section, okay. Moment curvature relationship gives me the capacity of the section, okay, it gives me the capacity of the section, okay. Moving ahead, the resistance and stiffness functions, okay. For a single span beams, we use a single degree of freedom analysis for the flexure response. As we have seen earlier in the examples, we use a single degree of freedom analysis methods, okay. For resistance, okay, we calculate the resistance at the ultimate load and the stiffness is calculated by the initial slope, okay, and this is defined by a bilinear load deflection curve, okay. So, this is for a single span beam, okay. For a single span beam, okay, this might be the resistance function Ru, okay. So, Ru determines the ultimate load, okay, and stiffness is determined by the slope of this curve, Okay. For a continuous beam, okay, meaning a multi-span beam, so mechanism of collapse involve formation of the plastic hinges. What does it mean? Okay, if we have a single span beam, okay, let us say we have a simply supported beam, okay. So if one plastic hinge forms, okay, it means that if we cut out this section, if I look into the cross section, the full plastification has taken place, okay. So here we say that the plastic hinge has formed, okay, and after the formation of one plastic hinge, ultimate capacity of the section will be reached, okay. For multi-span continuous beams, okay, or beams having more number of redundancy, okay, there is a need for multiple plastic hinge formation, okay. So this multiple plastic hinge formation will depend upon the cross sectional properties of the section, okay. Let us say we are talking about a fixed section, okay, or a section that is continuous over one or two spans, okay. Okay. So in order for the formation of the full mechanism, okay, more than one number of plastic hinge formation needs to take place, okay. So this might be the formation of the plastic hinge at location 1, plastic hinge at location 2 and plastic hinge at location 3, depending upon the cross sectional properties of this section, cross sectional and the material properties of this section, okay. So once all the three mechanisms has been formed, okay, then only the system is said to have reached its ultimate capacity, okay. So here, depending upon the location of the different plastic hinges, okay, this will be the value of my, this is how the R will change with respect to the deflection, okay. So the mechanism of collapse involve formation of plastic hinges, okay. So here one plastic hinge will be formed and here multiple formation of the plastic hinge will be required, okay. So economy favors simultaneous hinge formation along span, okay. It means that, let us say I am dealing with a fixed beams, okay. So here first, for the sake of economy, we have to design in such a way that the two plastic hinges, okay, are formed at the end simultaneously, okay. It means that this is the first formation of the plastic hinge and this is the second formation of the plastic hinge, okay. So this resistance curve will look something like this, okay. Formation of the first plastic hinge, formation of the second plastic hinge, okay. So formula for a two span beam, okay. So here, depending upon the different span configuration, different boundary conditions, the different formulation can be given, okay. So this is the equation for the two span beam, okay. Similarly, we can have the equation for the fixed beam and other boundary conditions, okay, and those equations are available in TM5 1300 or UFC 3340, okay. So all those equations are given there, okay. So the exterior span of continuous beam with 3 or more spans, this is the equation. Interior span of continuous beam with 3 or more spans, this is the equation, okay. So for different boundary condition, different configurations, we have the equations for the ultimate load, okay, and the corresponding stiffness, okay. So we can use any of them depending upon our circumstances, yeah. Whichever beams we are dealing with, we can take the appropriate formulation and can use them. So this is the chart that we were talking about, okay. So depending upon the configuration of the configuration of the beams, okay, I can use the equation for the ultimate capacity, okay. So all these equations are present in TM5 1300 and UFC 340, okay. So as per the appropriate conditions, the appropriate equations should be used, okay. Again, for the different configurations, okay, the equations for the elastic stiffness and the equivalent stiffness is also present, okay. So let us look into this case, okay. So here one plastic hinge is required in order to form the mechanism, okay. So if one plastic hinge is formed, the mechanism will be formed, okay. So the value of RU over delta, okay. So there will be only one slope, okay. So this is the slope, okay. So the elastic stiffness and the equivalent stiffness are the one and same. If you are looking into a, let us say we are looking into a fixed beam, okay. So if you are looking into a fixed beam, okay. So for the economy's sake, we are assuming that the first plastic hinge is formed at the ends, okay. This is the first plastic hinge and the second plastic hinge forms at the center, okay. So then it means that it will go and do something like this, okay. First plastic hinge formation and the second plastic hinge formation, okay. So this number will corresponds to the elastic phase, okay, and this number will corresponds to the K equivalent. Okay. So, this will be the K equivalent. Okay. It means that we are assuming that the system is behaving such that only one plastic hinge has formed. Okay. So, what we will do is that we will try to take the total area of the total area under the section. Okay. So, that we are getting the capacity, we will keep RUS same. Okay. And then we will calculate the equivalent slope. Okay. So, this is the equivalent slope. Okay. So, similarly, depending upon the mechanism, whether it is having one plastic hinge or more than plastic hinge. Okay. If it is having more than if it is having one plastic hinge, then the equivalent stiffness will be equal to the elastic stiffness. If it has more than one plastic hinge, then we will have to calculate the equivalent stiffness depending upon the plastic regions. Okay. So, this is how the equivalent stiffness is calculated. Okay. So, these are the load factors. Okay. Again, these load factors can be directly used to calculate the load factor, mass factor and the load mass factors. Okay. So, these numbers we can directly use to calculate the values. Okay. So, let us look into a design example. Okay. So, what we need to do? Okay. First, we need to calculate the ultimate resistance to match the prescribed deflection limits. Okay. So, this is the key step. Okay. Then for the dynamic load factors, okay, we have to use the dynamic load factor. Okay. 1 for 2 degree rotation, 0.5 for the large rotation, and we have to check for the appropriate resistance. Okay. Revise design using the response chart. Okay. So, first of all, what we need to do is that we need to calculate the natural period of the system. Okay. We need to calculate the effective mass and the effective stiffness. Okay. And this is used in the dynamic response chart to estimate the maximum dynamic deformation. Okay. So, when we are designing for shear, we have to calculate the yield capacity in the shear, okay, using this equation. Okay. And the stresses in the web should not exceed the dynamic shear yield stresses. Okay. So, these are the methodology for the designing of beam and for the blast loading. We also need to check for the local buckling criteria. Okay. Local buckling criteria of the flange end wave. Okay. So, in the steel design, it is important that this buckling criteria is being checked. Okay. To ensure that a steel beam will attain fully plastic behavior and attain the desired ductility at plastic hinge location, the elements of the beam, the individual elements of the beam section must meet the minimum thickness required sufficient to prevent a local buckling failure. Okay. So, there should not be any buckling in the flange and there should not be any buckling in the web. Okay. So, these are the criteria. Okay. Okay. So, let us look into an example. Okay. When we need to design a simply supported beam. Okay. So, criteria given. Okay. So, this is the criteria as per the functional requirement. Okay. So, this criteria will be as per the functional requirement. Okay. So, personal protection is required. So, the support rotation allowed, okay, it is limited to 2 degrees. Okay. So, here the limit is this theta is limited to 2 degree. Okay. It should not be more than 2 degree. Okay, from the personal protection criteria. Okay. Then we choose the material, we choose 36 KSI steel, and this is the Young's modulus for that particular steel. Okay. Weight of the decking. Okay. So, the decking element. Okay. So, the decking element that is kept on top of it has a weight of 48 pounds per square feet. Okay. And this is the load criteria. Okay. So, this load criteria we have already seen how to calculate the load criteria. Okay. From the actual pressure. Okay. How to change from the incident pressure, the reflected pressure, and from there. Okay. We have seen how to make the Friedlander's profile. Then we have seen how to make the equivalent loading profile, and then apply this loading profile in order to calculate the loading on the different faces of the element. Okay. So, from there we get this loading curve. Okay. So, first we calculate the equivalent static load. Okay. So, for the low pressure blast cases, okay, so we assume that the equivalent static load equals peak pressure. Okay. So, whatever is the peak pressure, we will design for that. Okay. Why? Because for the analysis, okay, for the analysis we need on the x axis we know that we need the value of T divided by Tn, okay, T we will get from this number. So, T becomes 40 millisecond. Tn, we require Tn. In order to calculate Tn, we require our K star and M star. Okay. So, K star and M star will come from the sectional properties. Okay. So, in the sectional properties, we have the length, okay. We have the length, we have the material properties, okay, but we do not have the cross sectional area. Okay. So, in the first step, we need to assume a cross sectional area. Okay. So, since we are asked, since in this particular analysis process, okay, first we need a cross sectional properties, okay, in order to calculate the time period of the structure. Okay. So, either what we can do is that we can have a random guess, okay, but if we have a random guess, then we might have to do more iterations. Okay. So, in order to have a first estimate, okay, so in order to have a first estimate, what we are assuming is that we are taking the applied pressure, okay, as the equivalent static load. Okay. So, we get the UDL, okay, we get the UDL that is applied on this particular beam, okay, assuming the equivalent static load is equal to my peak pressure. Okay. So, we calculate the uniformly distributed load, okay, where 6.5 is the peak pressure coming from here, 4.5 is the width of the beam, and 144 is the unit conversion. Okay. So, step 1, a preliminary estimate. Okay. In order to have a preliminary estimate, we are equating the pressure with the equivalent static load. Okay. Once we have this equivalent static load, okay, so we can calculate the required plastic moment. Okay. So, for a simply supported beam, okay, we know that this is the equation for the plastic moment. Okay. So, we get the applied load. Okay. Okay. Once we have the applied load, then we will calculate the resistance of the member. Okay. So, dynamic design stresses, as we have seen earlier, we calculate using this equation. Okay. We multiply the appropriate factors to increase for the dynamic loading, okay, and then we calculate the required section modulus. Okay. So, what we can do is that since in this particular case, okay, a requirement of personal protection of 2 degrees is meant. Okay. So, in this particular case, the requirement is limited to 2 degrees. Okay. It means that we are in a region where u is typically less than 3. Okay. So, here we are assuming that our section is under the elastoplastic case. It means that it has gone beyond the elastic case, okay, but it has also not reached the fully plastic case. Okay. So, it is somewhere in between the elastoplastic region. Okay. So, my section is behaving something like this, okay, in the elastoplastic region. Okay. So, that is why we are taking the average of the section modulus, okay, average of the modulus in the elastic range plus average of the modulus in the plastic range. Okay. So, we are taking this configuration, okay, average of the elastoplastic range. Okay. So, using our design chart, okay, we have the values of our, okay, we choose a section, okay, let us say we have chosen a section. Okay. So, because here we have the value of MP, okay, we have the value of MP as 152. Okay. So, this becomes 152 and we have the value of FDS, okay, that is 51. Okay. So, we know the required sectional capacity. Okay. So, from the design chart, okay, we can choose for a appropriate sectional properties. Okay. So, from there, okay, we can use this way also, or you can calculate the MP also and calculate the required moment capacity. Okay. So, using an appropriate section, we can have the first estimate of the section. Okay. So, this becomes our first estimate of the section. Okay. And then we check for the local buckling, and we check for the web buckling, we check for the flange buckling. Okay. So, if this passes, then we have the first estimate of the section. Okay. So, once we have the first estimate of the section, then we can calculate the effective mass, that is m star. Okay. So, we have the effective mass, that is the m star, then we have the appropriate mass and load factors. Okay. So, using the mass and load factors, we calculate our m star and k star. Okay. After calculating our m star and k star, we can calculate our natural period of the system. Okay. So, we have this quantity, we have the natural period of the system, t was given to us, okay, 40 millisecond, okay, that was the requirement in the given statement. Okay. So, t was given to us, okay, and t over Tn is given to us. Okay. So, we have the equations for calculating the total resistance of the system, okay, and we have the applied loading on the system. Okay. So, using this two, we have our ratio of RU over P. Okay. So, this is 1.1. So, we choose the appropriate curve. Okay. This is the curve. Okay. So, here 1.22. So, 1.22 and this curve. So, we get this number, and from here we will get the value of xm over xc, okay, which is approximately 2, okay, which is written out here. Okay. So, once we have the value of xm over xc, okay, we know how to calculate our xc, okay, Ru over Ke, okay, the resistance divided by my stiffness, and I have my total xm, okay, and depending upon the configuration, I choose my, depending upon my configuration, I calculate my rotation. So, rotation is 1.43 degrees, which is less than my allowable limit of 2 degrees. Okay. So, this section will survive, the chosen section of the chosen section, okay, this initial choice what we got W12 cross 26, this will meet our requirement, W12 cross 26 meet the requirement. Okay. Then we check for the shear stresses. Okay. So, here we check for the shear stresses. Okay. So, this is the maximum, this is the capacity of the shear, and this is the maximum support shear. Okay. So, the capacity is greater than my requirement. Okay. So, then the shear check is okay, shear check is okay. Okay. So, in the first step the rotational requirement was okay. Okay. So, from there we move for the shear check is also okay. Okay. So, we go back and look into our problem statement. Okay. So, the shear check is okay, and for the flexure check we check for the rotational requirement. So, both these checks are okay. So, it means that my chosen section, the initial choice of the section is okay. Okay. So, if it fails, okay, in either of the requirement, the rotational requirement or the shear requirement, then what we need to do is that we need to go back and increase the area of the section. Okay. So, in this way we design for the steel section. Okay. Similarly, we will look for the design of the concrete section. Okay. So, similar to my steel section, these are the tables given to increase the amount of design stresses. Okay. So, this is the increase factor used for the multiplication of the design stresses, okay, from the yield stress to the dynamic design stress. Okay. So, these are the factors that can be used. Okay. So, depending upon different bending action, tension action, okay, shear action, okay, different factors are been given. Okay. So, again, for the use of different support quantities, okay, the limitation for the different support rotation, the different values of my design stresses are been given. Okay. So, maximum reinforcement requirement. Okay. So, whatever code we are using, okay, so depending upon that code we will have to check for the maximum reinforcement requirement and the minimum reinforcement requirement. Okay. So, this becomes code dependent. Okay. So, this becomes code dependent. It means that in no case, okay, my minimum steel reinforcement ratio should be less than a particular value, or it should be overclocked. Okay. Because in the concrete design we need a balanced condition. Okay. So, we do not do an over design of my section. Okay. We always are designing for an balanced condition or under designed section. Okay. So, let us look into one example. So, here similar to the previous case, equivalent loading has been given. Okay. So, first what we need to do is that we need to choose for the initial section. Okay. In both the cases, an initial choice of my section is required. Okay. So, what we do is that we take the applied loading, okay, as my equivalent loading. Okay. We multiply the stresses by the respective quantities to get the dynamic stresses. Okay. So, we calculate the dynamic strength. Okay. So, for beam in the bending, okay, for depending upon the rotation criteria, we need to calculate the dynamic strength. Okay. So, once we have the dynamic strength, okay, what we can do is that we can have a choice of the initial section. Okay. So, we can choose for the initial reinforcement ratio. Okay. So, once we choose the initial reinforcement ratio, okay, then we can choose for the maximum and the minimum reinforcement requirement. Okay. Once we check for the maximum and minimum reinforcement requirements, okay. So, what we can do is that we can put steel, okay, we can put steel, okay, so that it is somewhere in between these two quantities. Okay. So, this can be treated as our first estimate. Okay. So, putting a steel quantity that is in between the min and the max requirement. Okay. After that, we can calculate the capacity of my section depending upon what is my boundary condition and the configuration. We can calculate the capacity of my section. Okay. We can calculate the ultimate capacity, negative moment capacity and the plastic moment capacity. Okay. And from here we can calculate the ultimate resistance. Okay. So, in this particular case we are assuming a fixed condition. Okay. So, for a fixed condition, okay, so this is the case applied and this is being used here to calculate the ultimate capacity of my section. Okay. And after that we calculate the modulus of the concrete. Okay. Steel modulus we already know, we calculate the modular ratio, okay, and the coefficient of second moment of area for the cracked sections is also calculated. Okay. So, this graph is used to calculate the coefficients. Okay. So, from there we calculate the crack moment of inertia coefficients, okay, and then we calculate the average second moment of area, okay, and we also calculate the gross second moment of area. Okay. Okay. And using all these numbers, okay, we calculate the equivalent stiffness. Okay. Remember we were using the fixed beams. So, from the fixed beams using these charts we calculate the my equivalent stiffness of my section. Okay. So, once I have my equivalent stiffness of my section, okay, we have calculated the capacity of the section, we have calculated the stiffness of the section. It means that we can calculate the elastic deflection of the section. Okay. And depending upon the rotation, okay, and the deflection allowed, we are assuming that my section is remaining in the elastic region, elastoplastic region or the plastic region. Okay. So, here we are assuming that my section is in between the elastoplastic and the plastic region. Okay. So, we calculate the equivalent load factor, load mass factor, and once we have the equivalent load mass factor, we can calculate the time period of the structure. Okay. Once we have the time period of the structure, okay, the time period of the loading was already given to us. Okay. So, using this chart, okay, we have already calculated the capacity of the section, we can calculate the loading applied on the section. Okay. So, using 1.49, okay, somewhere here, RU over P is 0.77 somewhere here. Okay. So, 77, so between 0.7 and 8. Okay. So, somewhere around here. Okay. So, we calculate the ratio of XM over XC. XC we have already calculated. Okay. So, we can calculate the value of XM. Okay. And from here we can calculate the angle. Okay. So, the angle is 0.2 degrees, okay, which is the less than the requirement of 1 degree. So, the chosen section is admissible. Okay. So, in this way we can calculate the steel section requirement and we can calculate the concrete section requirement. Okay. First step, what we can do is that we can use the applied pressure as the equivalent loading and get an initial section. Once we have the initial sections, we can calculate the sectional properties, we can calculate the resistance of the section, applied loading we have been already given. Using the quantities in the charts, we can calculate the maximum deflection of the section, and from the maximum deflection of the section we can check for the requirement. If it meets the requirement, then our section is okay and we can go ahead and check for the other capacities like shear capacities. If it is not okay, then we have to revise the section. The same methodology we can follow for the design of the concrete and the steel beam both. Okay. So, I advise to practice the design example as been given. Thank you.